Welcome UG students. We are now going to that of the CUET solution 2022. This is very important examinations in the in India for the entrance in that of the MSc and PhD level. Now we are going to that of the first slide about the 2022 solutions of the CUET questions. When two sigma bonds on the same carbon cleave, the following chargeless carbon species are formed that can react with that of the produces the different type of the benzynes only, carbene only, nitrogen only, or both carbene and benzynes. We know that carbene is the chargeless sextet species which can eliminate the two groups from that of the same carbon atom by the reaction with that of the base. Here the OH minus can cleavage the CH bond, produces the negative charge, and then this negative charge can cleave the CCl bond, produces the carbene. And this is the sextet species contain the 6 electron and very unstable species, and it can react with that of the different type of the organic molecules to form the different type of the products. So here the option, correct option is that the carbene is the correct option, where the same center produces by the cleavage of the two bond produces the carbene species. If the carbene is the two species, one is the singlet carbene and another is the triplet carbene. In case of the singlet carbene, there are two electrons present in the opposite spin, and one orbital is vacant one, so it readily form the two bond to give that of the cyclopropane molecules. The addition is the highly stereospecific additions. But in case of the triplet carbene, the two electron present in the parallel orientation, so there is possibility for the two bond formation by the 2A, and we get that of the cis and trans cyclopropane derivatives. Since the two products are formed, so it is the non-stereospecific addition. Since it is only one product are formed in case of the singlet carbene, so it is the stereospecific addition. This is the examples of the Simon-Smith reactions where the carbene is formed in the reaction medium in presence of the zinc and copper. Here the zinc and copper cleave the I minus, and two groups are eliminated to form that of the carbene species. And if the hydroxyl group is present, the coordination of the zinc atom with that of the hydroxyl group, so the cyclopropane always come to that of the same phase to that of the hydroxyl group and produces the corresponding cyclopropane derivative in the same phase with that of the hydroxyl group. Rhodium tetraacetate has been also used for the preparation of the carbene derivative from the diazonium salt. Here the diazonium compounds react with that of the rhodium tetraacetate to form the carbene derivatives, and the CH insertion to produces the cyclopropane derivative with the trans stereochemistry. Now we are going to that of the second questions. One is the regions and assertion questions. In the region and assertion questions, here assertion is that cyclopropane is more prone to undergo ring opening reaction than cyclobutane. We know that the cyclopropane has greater strain due to that of the inner side angle is the 60 degree, but this is the sp3 hybridized, so the outer angle is 109 degree 28 minute. So the severe angle strain, that is the 24 degree 44 minute angle strain, will appear in case of the cyclopropane system. So the cyclopropane is highly strained molecule, and it is easily cleaved by the any type of the reagent, by any type of the acid, to form that of the highly reactive species compared to that of the cyclobutane, as the angle strain is lower in case of the cyclobutane. But in the second case, according to Baer strain theory, cyclobutane is more highly strained than cyclopropane. We know that this is the order of that of the Baer strain theory, where the cycloalkane, cyclohexane, cyclobutane and cyclopropane. That is, cyclobutane is more stable than cyclopropane. So the region is not the correct, but the assertion is true. So the A is true, but R is false. Next question is that of the elimination questions, where the elimination E2 reaction in the statement question, statement 1 is the E2 reaction follows second order kinetics and are not accompanied by rearrangement And statement 2 is the E2 reaction show large hydrogen isotopy effect. We know that the E2 reaction is the cleavage of that of the CX bond with that of the ETO minus, and the reaction E2 reaction is the one step reaction where the two groups can be eliminated in concerted manner and produces the alkene product. If the carbocation is formed, then the rearrangement will occur. Here the carbocation is not formed, so the rearrangement is not take place in the E2 reaction, and the reaction is also depends on that of the substrate with that of the base. So the E2 reaction follow the second order kinetics. Again, in case of the E2 reaction shows large hydrogen isotopy effect, if we see that of the if the hydrogen is substituted by the deuterium, and if we measure the KH by KD ratio, since the CH bond is back in the RDS, so the KH by KD ratio is always greater 7.9 greater than 1, so it shows that of the primary kinetic isotopic effect. Hence, thus both statement 1 and the statement 2 are correct. And the elimination, if we see that of the energy profile diagram, here that this is the transition state where the base can capture the hydrogen atom and cleave that of the X minus and produces the transition state. Here the CH bond is breaking in the RDS. And we know that the E2 elimination is always that of the anti-periplanar orientation, where the HOMO of the CH bond can interact with that of the LUMO of the Cl bond, produces the alkene. But the anti-periplanar geometry is more preferable compared to that of the syn periplanar geometry. In case of the syn periplanar geometry, the base will capture the hydrogen and the Cl bond is cleaved and produces the highly sterically hindered transition state, which is highly unfavorable. So the anti-periplanar transition state for E2 elimination is more favorable. Now, if we go to that of the configuration, that is stereochemistry related problem, in case of the stereochemistry, we show that the Gavin structure converted to that of the Fischer projection, and here after the Fischer projection, we see that the hydroxyl group is in the first priority. This is becomes A, and the CHO group becomes B, and the CHOH becomes C, and hydrogen becomes D. So the two carbon is the A to B to C in the anti-clockwise direction, and hydrogen go to that of the horizontal. This is opposite to that of the very good rule, that is the hydrogen in the front side. So the configuration is 2R configuration. Similarly, if we see that of the C2 center, in C2 center the OH group the A, and the CHOH group is the B, and the CHOH CH2H group the C, and hydrogen is the D. This is also anti-clockwise orientation. Hydrogen group is the horizontal direction, so it is R. Similarly, the fourth group is also R configuration. So the option 1 is the correct. Now we go to that of the aromaticity questions. Here the different type of the aromatic. Here the matching problem is there. In the matching problem, if we see that of the first question, that are cyclooctanyl trinyl cations, here the one carbon is the sp3 and another carbon contain the positive charge. This is the partially conjugated, contain the 4n plus 2 pi electron. We know that the partially conjugated system is homoaromatic nature, so the A is the homoaromatic. In case of the B compound, the cyclopentadienyl cation, cation contain the 4n pi electron, so it is the anti-aromatic compound. Now we go to that of the C problem, C structure. Here the cyclopentadienyl anion contain the 6 electron, so it is aromatic compound. But in case of the D, there is no conjugation and the contain 4n pi electron, so it is non-aromatic. So the matching problem is that the 4 option is the correct option. Here given the some typical aromatic compounds where the 4n plus 2 pi electron is present. In case of the cyclopropenyl cation, the 4n plus 2 pi electron is present, so it is aromatic compound. But the cyclobutadiene does not contain the 4n plus 2 pi electron, so it is not considered as the aromatic compound. Rather, it is considered as the anti-aromatic compound. The benzene is the aromatic compound, but the 8 pi electron, it is not considered as the aromatic compound. But this is the structure of the azulene. We know that the azulene can be polarized to form the 2 is the 6 electron by the polarization effect. Here the pi electron is conjugated and the negative charge is created in the cyclopentadiene ring, and the positive charge is get in the cycloheptatrinyl ring, and we get that of the two ring system is in the aromatic. Now the second statement problem is that the substitution problem. Here the rate of statement 1, the rate of SN1 reaction depends on both the carbon skeleton and the nucleophile. We know that if we see that of the kinetics of the SN1 reaction shows that the rate of the reaction is only depends on that of the substrate but not the concentration of the nucleophile. So the statement 1 is correct, is not correct. That is the here shows that the SN1 reaction depends on the both carbon skeleton and the nucleophile. The SN1 reaction did not depends on that of the concentration of the nucleophile. In case of the statement 2, the rate of SN2 reaction depends on the carbon skeleton, the leaving group and the nucleophile. If we see the kinetics of the SN2 reaction, here the nucleophile concentration and the substrate concentration forwardly increases with the increasing the rate with the concentration of the substrate or with the concentration of the nucleophile. So the SN2 reaction depends on that of the both substrate and the nucleophile. So the statement 1 is false, but the statement 2 is correct. Now we go to that of the nucleophilicity. If we see that of the nucleophilicity problem, here the pH O minus is which of the following nucleophilicity is not correct. Is not correct means the ethoxide ion is more nucleophilic than OH minus. We know that the ethoxide has plus I effect, increase the electron density on the oxygen atom, so it becomes more nucleophilic compared to that of the OH minus. Ammonia is also more nucleophilic than water, as the nitrogen atom is less electronegative, so it has greater tendency to donate electron to that of the electron deficient center. Now if we go to the pH O minus and OH minus, here shows that the pH O minus is more nucleophilic than OH minus. This is not correct, as the pH negative charge on the oxygen atom is conjugated over the benzene ring, so the negative charge is not accumulated on the oxygen atom, so it is not the higher nucleophilic. Compare OH minus is higher nucleophilic than pH O minus. Again I minus is more nucleophilic than bromine minus. If we go from that of the top to bottom with increasing the size of the nucleophilic pieces, the I minus becomes more nucleophilic than Br minus. Similarly, if we say that of the acetate ion and ethoxide ions, in case of the acetate ions is not the more nucleophilic, as the negative charge is more conjugated, so the ethoxide ion is more nucleophilic than acetate ions. Now we go to the chemoselective reduction. What is the chemoselective reduction? In case of the chemoselective reduction, the different type of the carbonyl group can be reduced chemoselectively compared to that of the other functional group. Here the lithium aluminum hydride, if we there is greater tendency for the reduction of the all type of the carbonyl group. Here the ester group can also be reduced and the carbonyl group also reduced. But if we see that of the different type of the reducing agent, that is the sodium cyanoborohydride, sodium borohydride, lithium borohydride, lithium aluminum hydride, the different type of the hydride donor produces the different type of the reactivity. But the sodium borohydride only reduces the aldehyde group, but it has not capable to reduce the ester group. So it is the chemoselective reduction. Here the aldehyde group is reduced, but ester group is not reduced. Now if we go to that of the next problem, that is the substitution versus elimination problem. Here the reaction between the methyl bromide and sodium tertiary butoxide leads to that of the tertiary butyl methyl ether. Here the tertiary butoxide has sent to attack with that of the methyl iodide, produces the tertiary butyl methyl ether. If we give that of the opposite orientation, that is the methoxide ion is taking instead of the with that of the tertiary butyl iodide, here the elimination product is formed compared to that of the substitution product, that is the O minus can attack with that of the carbon atom and cleave the I minus. So here the elimination product is preferred. So this route is not preferable compared to that of the tertiary butoxide ion can react with that of the methyl, produces the tertiary butyl methyl ether. And we see that if we compare the substitution versus elimination reaction, we know that the elimination reaction is more preferable when the base becomes stronger, but the substitution reaction is more preferable when the base becomes weak, that is nucleophilicity becomes higher, basicity becomes weak. So the elimination, the branching effect is also important. With increasing the branching, the elimination reaction is more preferable compared to that of the substitution reaction. If we increase the temperature, then the elimination reaction is more preferable compared to that of the substitution reaction. Now we go to the identification of the function group. This is the practical related questions, where we know that the different type of the ketones can react with that of the amines to produces the oxime or various type of hydrogen imine derivatives by the elimination of the water molecule. And if we see that of the aldehyde react with that of the hydroxylamine to produces the oxime derivatives, aldehyde react with the hydrazine to produces the hydrazone derivatives, aldehyde react with the phenyl hydrazine produces the phenyl hydrazone derivatives, and aldehyde react with the semicarbazide produces the semicarbazone derivatives. Now we go to the acid strength questions, where the different type of the acid groups can, here the paranitrophenol is more acidic than phenol. This is the correct, means the simple conjugation of the phenoxide ion with that of the nitro group, but paranitrophenol is acidic than 3,5 dinitro 4-nitrophenol. This is the 3,5 dimethyl 4-nitrophenol has higher steric interaction, so its acid strength is not higher as the negative charge is not conjugated. So this becomes paramethoxyphenol is more acidic than phenol. Phenol are more acidic than alcohol, means phenol are more acidic, means phenol the conjugate negative charge is created on the conjugate base, so it becomes more acidic. So option A, C, E only is the correct. Now we go to the Beer-Villager oxidation product. Here the Beer-Villager, we know that the Beer-Villager oxidation after the par acid can attack to that of the carbonyl, and the alkyl group is migrated on the oxygen atom, produces the ester group. Here the migration aptitude is that the hydrogen is greater migration aptitude compared to that of the tertiary alkyl, then cyclohexyl alkyl, then secondary alkyl. So if in the given problem the phenyl group has higher migration aptitude compared to that of CH3, so A product is that of the phenyl acetate, and in case of the tertiary butyl and the phenyl, the tertiary butyl group has higher migration aptitude than phenyl, so the tertiary butyl group is migrated on the oxygen atom, we get the tertiary butyl benzoate. So the option 2 is the correct. Thank you for watching this video.